Hello everyone, welcome back. So today I'm going to be talking about cell transport, or as I like to call it, cell transportation. So this is basically how substances enter the cell through the cell membrane. So they can either enter passively through the plasma membrane, or they can enter through those protein channels or protein carriers. And we always say, especially when it comes to passive process, that the concentration gradient will move from an area of high concentration to an area of low concentration. So again, there are two processes, so basically two ways that substances are going to use to enter into the cell, and that is going to be passive and active. The main difference between passive process and active process is that active process will require energy, while passive will not require energy, which is ATP. So under passive process, there are three types, and that's going to be diffusion, osmosis, and facilitated diffusion. So like I said earlier, these substances are going to be moving, substances or molecules are going to be moving from an area of high concentration to low concentration. We also use the term they're moving down the concentration gradient, or they're moving with the concentration gradient. So here we can see the ion channel, substances are passing through the ion channel to enter the cell, and then there's also a carrier protein that substances will use in order to get inside the cell. So the first one I'm going to talk about is going to be diffusion. So this is diffusion of solutes. This basically means that there's a passive spread or movement of these particles. So I have a picture here of, spraying a scent, a perfume. And inside the bottle, you're going to have the highest concentration of that substance in there. And by the time you spray it, then we say it's moving from an area of high concentration to an area of low concentration. We can also use the example of a perfume. If you have a perfume or a scent inside the bottle, let's say you open it, you're automatically overwhelmed with the scent. But if you spray it, then it's not so overwhelming. And then this is another example of these molecules or these particles moving from an area of high concentration, which is inside the bottle, to an area of low concentration. And one of the unique things about diffusion is that it has to occupy the entire space. So I have here, let's assume we have a dye. We put a tiny dye, we put it gently inside this water, and we leave it. You don't have to really do anything. You don't have to shake it. You don't have to do anything, basically. And as time goes on, you will see that the entire water will be filled with this dye. This is another example of diffusion in the particles moving from an area of high concentration to an area of low concentration. So all of the nook and cranny of these water molecules will be covered, or the bottle will be covered with this particle. Lipid soluble particles, they easily diffuse through plasma membrane. They don't really need a lot of work. Think of the phospholipid bilayer. So like becomes like. So lipid particles, the plasma membrane's lipid is made up of lipid. It's going to be very easy for particles to diffuse in. Also, smaller particles like oxygen, carbon dioxide, this is how they enter and exit the cell. Diffusion is also affected by temperature. For example, let's say you have like your iced coffee and you put sugar in it. If it's going to take a lot longer for the sugar to dissolve than if you have your sugar in a hot coffee, right? So this is how diffusion, temperature is affected by diffusion. And diffusion is also affected by concentration. The more concentration of a particle or substance that you have, the faster it's going to be for that substance to diffuse. And the molecular size, so faster a molecular heavier substance that has a heavier substance, which means having a bigger molecule size, will take a lot longer than than a substance that has a smaller molecular size. So the next one is facilitated diffusion. So with facilitated diffusion, this one is split into two: channel mediated and carrier mediated diffusion. I like to use the example of, like, let's say you have a little old lady trying to cross the street. She doesn't want you to carry her. She might just kind of say, can you just help me cross the street? Like I said, she doesn't want you to carry her. She just needs a little bit of help to cross the street. So this is an example of facilitated diffusion. So under channel mediated diffusion, water moves through these water channels. This is how water is going to get inside the cell. Water is going to be very difficult for water to pass through the phospholipid bilayer. So we actually use a special water channel called aquaporins. Ions such as sodium, potassium also use these channels to enter the cell. And there are two types of channels: leakage channels and gated channels. And like the name implies, leakage always means it's open, so you have like a draw, you basically have sodium leaking in, or you have potassium leaking out, while gated channels are controlled by chemical or electrical signals. So for the carrier mediated diffusion, we're going to use bigger molecules, because if you remember, I said smaller molecules can easily diffuse through the plasma membrane. But what about substances like glucose, amino acids? They're going to find it very difficult to get through the plasma membrane, so they're going to use a helper called a carrier. It's literally going to carry these glucose molecules inside the cell. All right, so we can see here a glucose transporter helping to get glucose in the cell. The next one is going to be osmosis. Osmosis is the movement of solvent, which the universal solvent is water. No matter where you go in the world, if you want to dissolve something, the first thing they're going to recommend to you is water, right? So here, the only thing that's moving across the membrane is going to be the solvent, and it has to be a selectively permeable membrane, just like the plasma membrane. So the flow occurs when the water or the solvent is different on two sides of a membrane, and the water is going to move from an area of low solute concentration to a place of high solute concentration. All right, so I have here and this is very applicable. I'm going to talk about it in the next slide. Let's say you have a red blood cell and you place this red blood cell in water that contains salt. All right, in water that contains salt. So one thing that most people don't know is that our blood actually has salt. It's not just just blood. It actually has the same concentration as a normal saline, which is 0.9%. So let's say we put this same, but for the sake of teaching you about osmosis, I'm gonna let's assume that this red blood cell has 5% sodium chloride solution, and then we now place it in a solution, in a water solution that has 5% sodium chloride. So what's going to happen is that, as time goes on, there is still going to be movement of water. All right. However, the same amount that's going in is coming out. All right. So we're going to have an equal balance, and we're going to say that this water solution is an isotonic solution. The word iso means same. All right. So the cell will end up remaining the same, neither gaining nor losing water. So this is your typical IV normal saline when you go to the hospital that you see hanging in the hospital room. So another scenario would be, let's say we have 5% of salt inside this red blood cell, and then we have 10% sodium chloride outside. So what's going to happen with time is that, remember that I said that water will move from an area of low solute to an area of high solute. So water will actually move out of the red blood cell. And if you look at the water level increased a bit because the water came out, and this will cause the cell to shrink, or we use the word crenate. The cell will lose water. sometimes students find it hard to grasp this concept, and I always use the example, especially if you're a cook. Let's say you're trying to make soup and you put way too much salt. You're not going to say, oh, well, I'm going to have to throw it away. What you do is you add more water. But let's say you initially put 1 tablespoon of salt. If your friend now comes along and say, hey, so now that this soup was so delicious, does the concentration, the amount of salt change? No, it's still the 1 tablespoon. So, but the water basically diluted it. So this is kind of what's happening here. The water moved out of the cell to quote unquote make the solution less salty. All right, so we still have 10% salt outside the cell, and we still have 5% salt inside the cell. So we use the term hypertonic solution. The water solution, we call that an hypertonic solution because of what it's doing to the cell. So another scenario would be the hypotonic solution. In hypotonic solution, we still have the same red blood cell. However, we increase the concentration, the salt concentration of the salt in the red blood cell. Now it's 10%, and inside the water it's 5%. So water is going to move inside the red blood cell. And again, you're going to see that the water concentration, the water level went down, and the cell is swollen. It's bigger than normal. It's the opposite of hypertonic solution. Water is moving inside the cell, and if care is not taken, the cell will actually burst. So we use the term that the water solution, the salt solution, is hypotonic because of what it is doing to the cell. So the cell gains water, the cell swells, and can eventually burst. So this is one of the reasons why, for example, we do not give pure water, even if it's distilled water. We do not give it to patients, especially IV, because pure water, distilled water, contains 0 salt. So water from your cell, the red blood cell, will go out. So water will actually go inside the cell and will cause the cell to burst, all right, because there's more salt inside your red blood cell and 0 salt in the distilled water. So movement of water will be towards where there is more salt, in this case the only salt, which is inside the red blood cell. And what it will do to the patient's blood is that it will cause all their red blood cells to burst. We call this hemolytic anemia. So how this is applicable, this saline solution we're talking about. So I have here, isotonic solution, in that you're seeing the movement of the water as the same amount that's going in is going out. So the cell remains the same, and then we see this crenation, the cell shrinking, and then we see this big round ball of red blood cells because water went in. So like I said, the normal concentration in blood is 0.9% sodium chloride, which is the same concentration as normal saline. So how are these like hypertonic, how are they applicable? So let's say someone is stranded on an island, stranded in the middle, they got lost hiking, and their cells are dehydrated. They were finally rescued and they were so dehydrated. The solution we're first going to give them, obviously in a clinical setting, IV, is going to be hypotonic solution because their cell has shrunk. So we need to get their cell to look normal, to the normal level. So we switch them for just a little bit. This has to be monitored carefully. So we give them hypertonic solution so that water can enter their cell, and as soon as water enters their cell, then we switch them to isotonic solution. That's the maintenance fluid. However, the other scenario, let's say someone has edema, they're swollen, this lady's feet, we're going to give them hypertonic solution, or even in cases of like cerebral edema, we're going to give them hypertonic solution because we're trying to let water to leave their cell. But again, this has to be monitored carefully, because we don't want a situation where we got them we don't want a situation where their red blood cell will go from a swollen state to a shrinking state. We want it normal. So again, once their cell is back to normal, we switch them to isotonic solution, which is a maintenance fluid. So I hope this was very helpful, and thank you once again, and I'll see you again in my next video. Bye.